So, pause here and say quick shout out to Tinfoil Hat Society. Also, quick update here. Those of you who've been paying attention to my trading, just to give you some frame of reference. This is pretty amazing, but I bought here about a little under that. It's more like a few days back I bought, where was it? It was something like, dropped about $1. It was about here. Something like that. About there I bought. It's at 318 now. But I sold this day, right before yesterday, Wednesday, at about 314.41. I don't remember where exactly I bought. I bought somewhere around below 314. I bought something like here. And then I sold at 14.41. I made $10. If I sold it here at 318, it probably would have been $500, something like that. You know, you make these decisions sometimes and you're thinking, oh, you know, I better play it safe. Went up, might go down again, might dip down again, might as well take my cut while I can. Boom. You gotta be careful, you gotta pay attention to the news that, well, it's funny, it's like the news can make such a big difference. The more I think about it, the more I feel like maybe, I don't know, maybe I should be waiting for big news to wait for a big drop and then wait for it to bump up a lot. I mean, I could actually play right in here, play in these dips. I mean, these are pretty consistent. These are kind of independent of really big news. Really big news just kind of blows everything away. But playing in here is fine. Because like, I know the theory. The theory is it'll eventually come back. But yeah, it's pretty funny. If I held, it's a $500 decision right there. It's like, that's very funny. I got this way of, I couldn't have predicted that, right? I wouldn't have known. There's no way to predict that. I know things like this are going to continue to happen. And by the way, I did predict the bet that I lost $10,000 on. I predicted it'd be about 319, right where we're at right now. So I probably would not have lost that much money if I just stayed the course. Didn't need to lose that 10,000 if I just held my ground. Pretty amazing. Anyway, just want to update on that. Don't mind me just missing out on thousands and thousands of dollars. I'll figure it out though. I'm gonna start automating my trading. I'm so sick of doing this by hand. It's just depressing. Automate my trading and just dump money in and play those dips. That band trading, it's called. But yeah, that's relevant, and the reason is that somewhat relevant, and the reason is we finished the problems, so we're done. We're good to go. Also, oh, you didn't get. Oh my. Oh, I'm sorry. Oh my goodness. Come on, Will. That's embarrassing. I'm supposed to show you this. Alright, sorry. Sorry about that. I bought like somewhere around here. It was like here. Sold around 314.41. If I held until now, I would have made like $500. I sold like right before the day before. I was like mulling it over whether or not I should sell. And I was like, I better just take my pickings while they're coming. But I gotta start paying attention to the news more. If there's like a, you know, The negotiations with China, with China, as well as the negotiations with the other one. Negotiations with China, and the other one is negotiations with the USMCA. That's what it was called. That was signed. So I think that was there was a small bump at the beginning of the day I saw, and then it just skyrocketed. I think everyone FOMO'd, and then everyone sold. Everyone was like, "This is way too high. Short, 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 short," and then they bought back again. That's so funny. This is not organic at all, by the way. This is totally just like speculation. And the reason for that is because it's not slow, steady, like disciplined, calculated. It's just like, everybody jump in. Everybody get out. Everybody jump back in again. We don't know what to do. I'm just gonna ride it out. I could have made $500, but whatever. And if I had still had 10 grand, it would have been a lot more than 500. It would have been 1,500. No, sorry. It would have been about 3 times that. So yeah, about 1,500 would have been. Dang, man, I don't mind making $1,500 a day. That's not bad. Yeah, I want to start automating my trading. I don't want to do this, man. I don't want to think about it. I just want to like make more money than I would if I didn't do it in some more intelligent way, you know. Automate my trading and then work as an employee, and just, you know, once I get a good year, I could start managing money. It's great. It's a good time. Anyway, the reason why that's relevant, right? The reason why that's relevant is we finished the problems. So now I'm a Clojure extraordinaire. I'm a professional, after all. And so yeah, I could say reasonably learned Clojure, pretty far from like expert level. Neat thing about Clojure is like a lot of people that learn Clojure have like between 10 and 20 years of programming experience. So it's like a pretty, I don't want to say like austere, but it's got this kind of air about it that's like, it's very, not idealistic, but it's got kind of a lot of heart to it in terms of the engineering and the goal and all of that. I like it. It's definitely way more challenging, I found, than typical programming languages, but it's good. I like it. It's interesting. It's decent. It's challenging. I'm up for the challenge. Yeah, finished the problems. So we're just gonna go over them one by one here, and just to prove that we did indeed solve all of them, we'll just take a look here. If we run this, congratulations, you've solved the problem. See the solutions or share this. You've solved them all. Come back later for more. Alright, maybe I should start at like 160 and then 165. I said I'd start at like 165, but I don't actually know where I stopped. Subset and superset we looked at. That one we looked at already. Language of a DFA we looked at. Comparisons, okay. We'll go with this one. Then we'll just go piece by piece here. Any orderable data type, it's possible to derive all the basic comparison operations from a single operation. Any operator but equals or not equal will work. Write a function that takes 3 arguments, a less than operator for the data, and 2 items to compare. Function should return a keyword describing the relationship between the 2 items. Keywords to the relationship between x and y are as follows: x equals y equals x greater than y greater than, x less than y less than. Right, so given a less than operator, you can infer the other operators. The way that you do that is as follows, and that's what this question is asking. Like, would you kindly show how that can be done? Well, with the less than, you can say, okay, if a is less than b, return less than, or this is what this conditional is, sort of like a fall through, a lot like a switch statement. A is less than B. Or you can just swap the order of A and B, and then suddenly it becomes a greater than question. And now if you're not less than and you're not greater than, then you must be equal. And so there you go. That's how you get less than, greater than, or equal. So, done. Pretty straightforward. Takes a little bit of time to think about it though. Takes some time to piece it together to realize it, but it's good. Oh no, this is a good one. This one was interesting. We looked at this the other day, so I have to explain it. It's kind of a lot of words for the explanation. So basically what they're looking for is imagine for a moment an infinite sequence of things, right? And then imagine actually even better than that, like imagine a matrix, sort of ij, we'll call it, right? 0, 1, 2, etc. And then also 0, 1, 2, etc. Right? Okay. The idea is that you can perform, so let's say our function just takes I and j and concatenates the two, starting with I, right? So you have 0, 0, 0, or 1, 0, or actually the other way around. Let's go, yeah, actually let's do it this way. Let's say j is on top. And then we're concatenating I with j. So you have 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2. Right? That's the result of your function. You can imagine this matrix going on infinitely. You could also imagine then saying, okay, let's not use a certain number of rows and columns, so we'll start our infinite matrix here. Right? You can imagine doing that too. That's the second operation they ask for. The first operation is they just want you to create a sequence of sequences where each sequence is infinite, and the sequence of sequences is infinite. And you're going to have what the sequence of sequences, what these values are in each sequence is. You're going to have to be given some function that takes two values, and that whatever that function returns is going to be the value in that particular cell. Right, so in this case we said we just concatenate the two, but you could use any function you want, any return value. And so our function is going to, we'll firstly generate this matrix as it is, this infinite sequence of sequences, infinite sequence of infinite sequences. Then alternatively, another function that will return this infinite matrix, but with a certain number of rows and columns removed. So starting at sort of a certain, it's almost like, so you could say, starting at a certain starting point, I guess, sort of somewhere in this matrix, right? And having it's still an infinite sequence. And then finally, the last function they want is, if you could imagine boxing off this infinite matrix and saying, okay, you're not going to go past a certain amount either. I realize these lines are getting kind of confusing. So you're not going to go past a certain point either, which makes this matrix, oh, that's, okay, makes that matrix finite, right? That's the third function they ask for. So that's what they're looking for in, like, sort of plain English. And they have some examples, but that's it. It's actually really straightforward what they want. So like this is like, if you generate the infinite sequence and then take a certain number of functions, certain number of values from each of these sequences, and then take a certain number of those sequences, right? So you take 6 of each, and then you take 5 such sequences, 1, 2, 3, 4, 5. Then you use the second function, which sort of does that. It doesn't do that. It actually starts at a different starting point, right? So we start at 3, 2, and then take 5 by 6, 1, 2, 3, 4, 6, and then this one sort of combines all of those. So now we're multiplying the values across, so you get a single digit rather than a concatenation. And it's going to start at 5 by 7, or no, start at 3 by 5, and you're going to take 5 by 7, right? So it looks like 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, right? So you don't actually need to. By the way, like, this question is kind of easy. You can kind of tell, like, oh, this 5-7 looks a lot like just this. Throwing that in front of whatever returns here, and then, oh, whatever this returns is a lot like just, excluding or creating sort of a starting point for your sequences. And that's kind of it. And then it's actually pretty easy after that. There is one little extra bit, which is they want these things to be, the class of these things to be lazy sequences rather than just cons. I was using cons of lazy sequences, as you can see, but then I just threw a lazy sequence in front, and that satisfied that. There's probably a much better way to do this, by the way, than the way I did it. But yeah, I almost copied directly what they had here for the test cases. So I said, all right, let me create a subsequence, which is just a lazy sequence, which is just the cons of a lazy sequence with this j incremented, where you cons f of ij, right? And then you're gonna have your sequences of sequences. You have some starting point, and you're gonna cons subsequences at that starting point, and then call this function again, right, itself, to create the next subsequence with this it's not a starting point, but it's sort of the I value incremented, right? So this subsequence increments the starting point j, and then this subsequence increments the row. We'll call it. This is sort of like the column value. This is sort of like the row value. So this one increments the row value, and these ones increment the column values. Basic way to think about it. And so you just start at 0, 0 here, and this could probably be done in a better way, but I really couldn't think of it. But we ended up with what do they call that? Rewriting this code a few times, which I think is fine, and then just throwing in m and n for the second case. These are multi-arity functions, so sort of 3 different function definitions. And then finally, I used that take map, those shenanigans that you saw here, as a way to make it finite after creating, sort of specifying the starting points. And there you go. Really simple. This is just kind of copied over 3 times. And let's see how it was done by others, right? Others definitely probably did a very good job on this. And we'll see. Right, here we go. 7 lines of code. Okay, so F call. Oh, I didn't think to do that. So F calls ls F with 0, 0. Right, so we. Okay, yeah. So you can save a lot. So you have this f of xy. This specifies the starting point. This one says, yeah, that's what I kind of did, but I should have thought of that, right? Just define it here and then have this one call this one. Oh, I didn't think of doing that. I feel kind of silly now. And then finally, this one also calls this one, but then adds this in front. And yeah, right. It's almost exactly the same. It's just this goes to. First we map here, and then we take, yeah. This is just kind of reversed, but it's effectively the same. Yeah, that's pretty funny. What he did here, though, this, I mean, I could have made these a little more succinct, I guess. It would have been like, I could just put this here, and then also put right, where m and n are sort of placed correctly, and then also this subsequence, I could have just placed this right in there, right? Basically just substitute these things in, and would have gotten effective probably the same thing here. Yeah, cons of this function. Yeah, it looks like he just kind of inlined the functions. I think it's better to kind of keep them somewhat separate, in my opinion. But actually, it's pretty clean. But it's effectively the same code that I have. It's just it's a little more cleaned up. Like I said, he made a little bit better use by calling this function. I didn't think to do that. I should have thought. I realized there was some way to do it, but I wasn't thinking about it. Thinking of it. Yeah, call this function. Make this one call this one. Make this one call this one, so I can collapse these and make them simpler. And then finally, I think I actually kind of prefer though have this spread out a bit though. It's easier to read, easier to understand. But yeah, I could have inlined it as well. It would have been just one line. It would look like this. Nice. Okay, well I don't feel so bad now. It's good to see a different solution, different approach. 69, 70, 71. Alright, this is a good one too. I can close these. So this one, I solved this one. Yeah, I think we talked about this. This is... Oh yeah, this is real awkward. I don't know if we talked about it. We vaguely talked about it. So yeah, we had these two right. No, we did talk about it. We did. Yeah. I just kind of wanted to get it to work. How do others do it? I'm curious. I'm also curious. 6 lines again. All right. Okay. Sort distinct. Oh, you could use distinct instead of using a set. I mean, not like it matters that much. It's kind of the same thing. Distinct. Is it really that different? I can also close this. Creating a set first. Okay, fair enough. It's like a set, I guess. Not really that big of a difference though. And then we're going to map list x to rest of x to create pairs. Now is this what I did? You can also partition 2-1. I think you get the same thing. Actually, yeah, I think this is correct. I think this is what you do. You can open up the REPL here. Take a look. So we could do like 1, 2, 3, 4 and rest of 1, 2, 3, 4. Let's see. Where was this? This is map list. Could think about it, but might as well just use the REPL and make use of it. Oh yeah. I like partition better though, it's a little more clear what's happening. Yeah, there you go. Okay. Fair enough. I think this is how I was doing it originally, anyway. Alright, so you get these pairs, and I got these bounds. Oh, look at that. Now that's interesting. Do we know these are positive integers? Now we're assuming these are positive integers. Now this was a problem that I ran into. This was difficult. No, never mind. No. Checking if the difference is -1. No, I take that back. If the difference is greater than -1, I mean, did it really matter? As long as it was not 1, the difference. And could have done it reversed or what have you, but yeah, okay, this is fine, I guess. This is pretty clean. So you take that difference is greater than -1. Or rather, -1 is, it's actually if the difference is less than -1. Meaning it's a more negative than -1. If the difference is more negative than -1, right? So they're not differing by 1. Filter that on the pairs. Okay, so that gives you the pairs that are sort of the breaking points, we'll call them, something like that, and the different bounds. That's what he calls them. Fair enough. And X bounds. Now this partition on the X bounds. Now this is really interesting. And this is super clean too. So how did he do this? Wow. Oh, holy smokes. This is even cleaner. So partition 2-1, sort of X. Partition all. Also didn't seem to care about things being equal either. Cons F first. What is this? F first. What does that mean? Oh, first. Okay, yeah, I guess that's useful. Don't use that too often. First. Cons this thing. The first of it is a... What is going on? And you apply this partition as a vector. Okay. Yeah, but what if you have an empty set, you know? And what happens there? I guess it's just nil. And then you remove all of the things that are B and Wow, this is kind of odd. So we don't care about duplicates here. And we say partition all. Each one of these, you're going to cons. No, it's not each one of these. It's just the sequence. You're going to cons with the sequence. The first of the sequence as a vector. Okay. That's fine. That's like the very first value that you get. That gets pushed to the beginning of your partitions. And that's what partition all does. May include partitions with fewer than n items at the end. Interesting. Oh, interesting. It did do partition 2-1, right? It did. But the last part maybe, it can't be. Because it's only stepping by one. This partition all is kind of meaningless. Do think this is kind of interesting though. We're going to remove all of the points that are have a difference less than 2. Meaning all of the if there is a B, yeah, these are actually the not just the breakpoints, but the, what do they call that? Not just the breakpoints, but the This is the opposite. These aren't the breakpoints that he's removing. He's removing the what do they call these? The points that have a difference of 1. All of those values, all of those sort of pieces that have a difference of 1. He's removing them right here. And then he's flattening everything that's left over and then partitioning into pieces of 2. Really interesting. Yeah, you need to have the first part, excuse me, because you might have the case where the first part is like, 4 to 6, so that doesn't get removed. But you still need 4 to 4 in the beginning. That's why he's throwing this piece in here. If it was 4 to 5, you would end up removing the 4, 5. And the very last element, let's say if we consider the last 2, if you had like 17, 19 at the end, if you had 17 to 18, you would also remove the 17, 18. Now that's kind of interesting. I think this just barely works on the test cases because none of the test cases end on a, it's actually incorrect. None of the test cases end on a, well, this one does. How come this one works? Hold on, never mind. It's not. I think it's wrong. I don't think it's. Well, I'm assuming it's not wrong because it works. But why does it work on that test case? This one. 1, 2, 3, 8, 9, 10. I know you get rid of the 1, 2, and the 2, 3, and then there's a 3, 8 that we keep. So we have 1 to 3. Then we have 8, 9, 9, 10. When we get rid of 8, 9, and 9, 10, we just have this 8, this 3, 8. We flatten, we get the 8 at the end. No. Three, 8, 8, 9, 9, 10. Why do we get 8 at the end here? What does this look like if we partition all 2, 1? Oh. Could open the REPL again. Takes a minute. Oh, no kidding. I take it back. Okay, so the partition all does. So, okay, so if you do take. Yeah, never mind. Okay, so you do append the first. Basically, you append the first and last 2 values. So there's a 1 appended to the front and a 4 appended to the back. So when you get rid of this 3, 4, you still have this 4 over here. I was wondering, I was like, what's the difference between just partitioning and partition all? Because that step at the end, when you go to 4, you do keep the 4. You don't just cut it off, where if you did partition 2, you would go 1, 2, step to 2, 2, 3, step to 3, 3, 4, and then step to 4, but cut off the 4 because there's no value afterwards. Partition all, you would actually process that 4. Okay, that makes sense. I was wondering, I was like, I'm missing something here. Something important. So the partition all appends that extra 4 at the end, or the extra 10 required at the end, as well as the extra value in the front. And then now you just remove all of the incrementing pieces, and then you can flatten the whole thing and partition by 2, and you're in good shape. So if you end on a 9, 10, you have an extra 10 at the end anyway, if you end on a 9-11, or should be like 17-19, then you have an extra 19 in the end as well. And so when you flatten partition, you get the 17 ends the thing to the left, and the 19 and 19 combine. Really interesting solutions. Really interesting. I mean, like I said, I did think there was probably some way to optimize this and make this a little cleaner, but I was kind of just trying to get it done, get on with it. I really like that solution a lot. It's very clever. Yeah, I guess adding the first element and adding the last element. I should think about doing stuff like that with these sort of sequence manipulation type questions. Should think about that a little bit more. What would it be like if you add the first element and the last elements to the front and beginning? I was also thinking of a succinct way to add those two, and I couldn't really come up with a good way, but this is good. I should use cons more often. Because I was thinking if it can join to the end, it converts it to a vector, and you have to add at the end of the vector, and then you have to convert it to a list, and then add at the beginning of the list, and I thought it'd be really awkward to do that. But it's actually not bad at all. Well, this one you initially you sort of begin with a list, and then you just add to the front of the list, so it's not a lot of extra overhead. So here, what do? We create these pairs, and we have these bounds. Now, this one is interesting. So this one removes the incrementing pieces. This part actually processes on the bounds. And it says, okay, you're going to flatten, and what you're going to flatten is going to be take the first, oh, that's very interesting. So this is the last and the first, and then the bounds. Oh no, these are actually the same. These are the same approach. They both remove the incrementing pieces, but this one gets the bounds and then processes this way, right? So this is how created a vector with the first value being set to the first of the sequence, and the last of the sequence of values. Oh, that's very interesting. Wow, look at that. Holy guacamole. Look at how they did that, both of them. And then flattens, right? And finally partitions on 2. That's amazing. I kind of like how this sort of just goes one to the next, but this is also really clever. These are both really good solutions. I like that a lot. But yeah, they call that a sentry, using a sentry. I think it's a sentry is it a sentry value? I don't remember. There's some name for that. The thing plopping something in the front and the back to sort of make the code cleaner. Without doing that, the code's a lot less clean. Although you could argue my code is a lot less clean. but even still, I think it still wouldn't be that clean. It's a pretty good solution, pretty cool. I should remember that for the future. So that's 172. Yeah, that was on my list of things to look at. So is this. About 173 or 171. 172. 73, destructuring, we'll go over this shortly. 74, 75, 76, 77. This one is an interesting one as well. 78. I think we did this, yeah, I should show you that. 180. And there was one question too that was very interesting that I solved recently as well. It was a medium question. It was, parentheses. This one. 195. Yeah, we're way. Yeah, this is. All right. I guess 188, 189, 190, 91, 92, 93, 94, 95. And how far are we supposed to go out here? I don't know, I guess problems get removed or something because there's like holes here. But anyway, so destructuring. This is kind of interesting. So sequential destructuring allows you to bind symbols to parts of sequential things, vectors, lists, sequences, etc. Let bindings, expressions, complete bindings. So all let parts evaluate to 3. Obviously you see the answer already, but the idea is that you're going to put something in here that's going to bind the stuff here, and then you can, those same bindings, when processed over here, gives you 3. So in this instance, what you can do is say, it took some guessing. Initially, it's like kind of an interesting little puzzle here, but starting from here is probably the easiest. So if you say increment is a function, 2 is a value, and this is a vector containing the function and then the value. So you might say, okay, what if I make f a function that we bind to, and then x a value 2 that we bind to? Well, then over here we're going to call f on x, right? And x is 2, and f increment 2 gives you 3, which is what you want. So in this case, f of x works. And then we say, okay, what does that work for the other ones? You say, all right, try f of x of b of, well, plus 1, 2. So what you end up with here is you destructure this piece to this piece, which is f and x. So f becomes plus, x is 1. So you have 1, f is plus, x is 1. And then you have b, which is binds to 2. So now b is 2, f is plus, and x is 1. And now plus 1, 2, or plus 1b, where b is binded to 2, gives you plus 1, 2, which is 3, right? So that's what you want here. Finally, you have bind, and I'm going to kind of go a little faster. You can bind f to plus, bind x to range of x, and then if you apply plus over range of 3, or apply f over x, apply basically takes the sequence and converts it to arguments to a function. So instead of having the sequence as an argument, you have a series of different arguments. So like if you wanted to do plus 1 and 2 and 3 as arguments, rather than plus over a sequence, you could do apply and give the sequence, and then it'll treat it as if it was plus 1, 2, 3. It's kind of a neat little function here, but yeah, obviously this works. So there you go. That's destructuring sequentially. There's also destructuring using keys and maps, which is very interesting too. But yeah, this helps make your code a lot more concise as well. Definitely like that. Definitely like that. All right, next, balancing brackets. I did solve this one. It was correct, but there's definitely a better solution. We'll take a look at the other solutions. We'll read the problem first. So, parsing a snippet of code, it's often a good idea to do a sanity check to see if all the brackets match up. Write a function that takes in a string and returns truthy if all square, round, and curly brackets are properly paired and legally nested, or returns falsely otherwise. So at first I thought this was harder. So you see they give you pieces of code and they have brackets and square brackets and curly brace brackets and all this stuff. And originally I thought this was a lot easier, or I thought it was harder even, I should say, because I was thinking of just matching up, like these would be valid and these would be valid, even though one is sort of contained in the other. Sort of a certain independence from one another that I was considering, but I was actually wrong about that. This is considered false, right? You see this not, this green means you want true, so you want not false, which means true. So this should actually give you false, so you can't nest them in this way. So actually it's a little bit easier, because basically all you need to do is push each time you see a brace of a certain type, push it onto a stack, and then once you see its counterpart, then pop from that stack. And then anytime you try to pop from the stack and the counterpart that you're looking at is not on top of the stack, you have an error and can terminate early. Anytime that you try to pop and there's nothing on the stack, you have an error and can terminate early. If you get through the entire sequence and your stack still has something on it, then you have an error and you return false. So not an error, but you just return false. If you reach the whole end of the function, the sequence, and you have an empty stack, that means you're in good shape and you're done. And those are sort of the different possibilities. It's like a very simple algorithm. All you've got to do, like I said, is just push when you see an opening bracket and pop when you see a closing bracket, and just match the closing bracket to the correct counterpart when you're trying to pop it. And then also just check that it's the correct thing to pop, that there is something to pop at all, and yeah, and then when you're done, just return whether or not the stack is empty. Right? If the stack is not empty, then it's false. If it is empty, then you return true. Super simple. And I sort of write that here. You could move this also outside of this loop, but yeah, I'd use a little bit of destructuring in the loop to get the head and the tail of this string, and also the stack, the initial stack. And I say, okay, let these brackets be defined as such. So anything that's in this counts as a bracket, and then I separate them further into closing brackets and opening brackets using, this is actually a map of the counterparts so the closing brackets to their counterparts. So the values are the opening brackets and the closing brackets are the keys of this map. So I just set that up quickly here too, opening and closing. And then I just said, okay, we're going to update the stack using this condition. If the thing we're looking at is an opening bracket, then just conjoin to the stack. If it's a closing bracket, then check if the stack is empty. If it's empty, return nil, which means terminate early. If it's not empty, then we're going to do a quick check that the top of the stack is equal to the right. Oh, yeah. Okay, this is kind of interesting. This is the map. So the top of the stack is equal to the counterpart of the head that we're looking at here. So we're going to get a closing bracket, and then we're going to check. It's going to map to an opening bracket, and we're going to check if the top of the stack is equal to that opening bracket. If it is equal, then we're going to pop that value from the stack. If it's not equal, then we return nil, and then we terminate early. If we don't see an opening bracket or a closing bracket, then we're done. Then we just return. I don't return, rather we're done. We're not done. I'm sorry. We just pass over that character and leave the stack as it is. And that's really it. Not it, but there's one more check, which is if the stack is empty. If the stack is nil, then we'll return false. Our stack is always not nil as long as we're still in a sort of quote unquote good state. So if it's nil, that means it's no longer in a good state, and return false. If we're at the end of the sequence, then we perform a check. We say, okay, if the stack is empty, return true. Otherwise, this obviously returns true if the stack is empty, false otherwise, right, as described previously. And then if we're not empty, that means we have more processing to do, so we recurse on the tail, or continue looping on the tail with the stack that we've got at present. And that's it. Super simple logic. Works, is correct. And we'll look at the solutions to get a better sense of how this might be done, or possibly how this ought to be done, so to speak. But I think I'm pretty satisfied with this overall. I think this is pretty clean. You know, it's obviously it's a bit verbose because I want to space things out a bit, but it's kind of easy to follow. So here we set up the character map. Is this open? Excuse me, I'm not really sure what's going on here. We'll look at the one that's super concise, I think. Yeah, these are all relatively concise. Assume 7. It's pretty good. Replace all. I don't know about that. I don't know if I really want to do that. Replace everything. Nah. Excuse me. Well, what does this do? Let's just think about it. Let RS take OS and replace OS with this. Then replace that with this, replace that with this. If RS is equal to OS, then check a nil, otherwise recurse. So what is this doing here? It's just saying This looks like regular expressions, I guess. So, oh, I think, what is, I think I know what's going on here. I think this is a, what's that called? This looks like you may be using, the context-free grammar as a kind of a production rule. This is sort of the regular, yeah, this is sort of like a production rule he's using. Repeatedly iterating a production rule. Technically, no, is that right? No, I don't know. Well, yeah, correctly placed parentheses can be considered to be, we'll call it a deque language. I'm not sure how to pronounce it exactly, but the deque language, which there's a context-free grammar that describes all of the correctly placed parentheses you could have, and further you could do you could sort of deconstruct. So you can sort of check if something does have correctly placed parentheses by repeatedly stripping away, sort of reversing the production rule for the deque language. We'll get more on that later, explain that later, but I think that's might be what he's doing here. So he's got this character, and then this not in here. Oh, I see. Yeah, that's exactly what he's doing. Almost exactly what he's doing. Sort of. It's basically stripping away all of these pairs, and he's saying, okay, just don't remove any character that's not these opening closing brackets. So this opening parentheses, closing parentheses. Not entirely sure why he needed these three characters. I guess that's something to do with the parser, but I think I understand. So remove all of the regular expressions that match this, which are initially an opening parentheses and then a closing parentheses. But now this is kind of interesting. If you had something like this, yeah, if you had something like this, this should be correct. But what would it do? His function here would replace, it would match every character here as many times that is not any of these. So, oh, I see. Yeah, it would still work because it wouldn't match these, but it'll match the inner parts first. So it'll sort of match on the inside. Oh, I see. Yeah, that'll work. The recursion kind of makes it. Oh wow, okay, this is a lot more clever than I realized. I didn't really want to look at it, but basically what he's doing is sort of brute forcing and saying, all right, just repeatedly match the inner parentheses or whatever brackets there are, right? The inner case. So in that repeatedly match the inner case and remove those sort of words, those pieces, until you can no longer remove them. And then if these are equal, then there's a check you've got to do. But you're very close to done. If they're not equal, then just keep going. So you're going to remove all these, and they're actually it removes the entire thing, right? So it doesn't just remove like the two brackets, it removes everything inside of the two brackets as well as a whole giant regular expression. It just gets removed. So it does that repeatedly. Here we check, this process is using a regular expression. It says look for anything in this set. So open, close, any one of these characters. It says look for one of these, and it says if it's nil, return true. If it's not, return false. So basically, after removing all of these, if there's anything left over, return false. If there's not anything left over, then return true. That's super simple. That's a lot cleaner, I think, than these other ways of doing it. Also, the way that I did it as well. I do like this quite a bit. It's definitely not that efficient, we'll say. It's not very it's not at all an efficient approach, but it is an interesting approach and very concise. Good for sort of short test cases. Classical stack problem. Yeah. The optimal solution uses a stack. And I thought this was interesting. I don't know if he used a zip map for this, but I was thinking about using opened and closed, and the reason I didn't is because there would be the map wouldn't be quite what I wanted. So what are some of the other solutions? What about this one that was 10 lines? So PB this one's a map, and this one's a set. Say if we're empty of this reduction, right, return true or false if we're empty in the reduction. I get the feeling this is just kind of like a much more condensed version of the same thing, which is not always the best. So head tail is x's of x. It's destructuring of this function, right? As x's. That's kind of what I did, head tail, and then have the x's in there, and then x is the next value, and you start with a sequence that's effectively empty. I guess it's supposed to be the stack. Conj, yeah, I guess this is sort of, you're gonna treat the list like a stack. The conj and pop will both be a head tail. Yeah, I guess it's not too bad. Do it that way. So you get x is s. So you process each character with this function. Head tail as x's of this sequence. That's kind of interesting. Okay. X's, so condition if p is equal to h, if ph is equal to x, then return t. So that's the tail, and p of h of the head is equal to x. So this gets the counterpart, right? So you get this opening bracket, there's a closing bracket as the result. If this closing bracket is equal to x, then you're going to take t. Now, I don't really know what this means or does. So this is the rest of the x's, I guess, for this sequence. It's a little weird. I don't really understand entirely what I'm looking at here. If not, then this bx, which is a set of x. So we failed the a couple things to note here. We failed the. There's a bunch of things to think about here. Okay, I think I understand. So if the head, which is so if this x matches what the head is the counterpart of the head, and the head would be an opening parentheses, counterpart would be the closing parentheses. If x is a closing parentheses, then you're going to return. Okay, you're going to remove the head. All right, I understand now. Okay, very confusing, but I get it. All right, this is basically removing from this sequence. If b of x, so if x matches an opening or closing parentheses, but clearly it's not the correct closing parentheses if it's a closing parentheses, you're going to conjoin x's with x. So you're going to say if it's an opening parentheses, we want to append it to our sort of stack. This will put it at the front. And then otherwise you want to just return x's, which is don't change it at all. The stack. It's confusing, I realize, but not too bad. So the tricky thing here is though, it seems like it might not be correct because this part, let's suppose you fail this check, and then we're checking it for empty. If we fail this check, we end up turning x's. So if this gets failed, right, then we're going to end up throwing something into the sequence that'll never be removed, basically. Can't be removed. Because the head will always be there's also another issue of like what happens if you try to pop when the stack is empty. What is this? This is P of H. So we take what's on top of the stack, you get the counterpart, check if the counterpart is equal to x. If it is, then we can remove the head. Otherwise you can't remove the head. And you either append the next thing, which then would need to be removed later, or you don't touch at all. Like what if this is a closing curly brace here? Right? Oh, I see. Yeah. Well, you actually would append a closing curly brace because you'll end up never removing that closing curly brace again. You'll always get nil for the top, and that would be the end of it. So appending an extra curly, which was equivalent to a pop. Oh wow, this is really interesting. I like this solution a lot. It's pretty clever. Pretty clever approach. It's very, very, very concise. Yeah, that'll put you in a faulty state all the way to the end if you try to pop something that's not already there, not able to pop. And then if you try to pop when it's empty, that's exactly, yeah, you'll end up pushing this on there. And that works too if it's empty, you try to pop, or if it's try to pop something that the incorrect thing to pop. If you, otherwise this just pushes, and then this will get popped appropriately later. So this just pushes everything on there. This will pop the correct things, and then never be able to pop it again if you try to pop when it doesn't work. Then this will always fail, and you'll always end up right here till the end. And yeah, interesting. And then obviously if there are things that weren't popped, that should have been popped, then this is not empty as well, so it handles both of those cases. Really clever. I had not thought of that, doing it this way. This is very, kind of takes some thinking as to like why it's correct, but it's very, very succinct solution. I kind of wouldn't want to write it this way just because it takes like kind of a lot of thinking to verify its correctness and understand what it's doing. It's succinct, but it's also like kind of heady, where this is like pretty simple. It's like pretty clear what's going on. Logic is not, it does the same thing, but the logic is a little different. This kind of relies on a little more nuance in terms of like how these things connect to each other, whereas this is like very explicit. I kind of prefer code that's a little more verbose, a little more explicit. Not much more, but a little more. If it's clear. You could argue that because there's not so many not so many extra words here, this is pretty clear, which I would agree with, but it is kind of hard to initially to understand how these connect with each other, these pieces, why it's still correct even though it's sort of doing it this way. Yeah, sort of a bunch of pieces connect together to make it up. It's pretty good. It's pretty good, not bad. I think we already hit our alarm here. So I'm going to go ahead and go to bed. But I do want to just finish off the rest of this here. We have 2 more lined up. So we have our best hand. I think we went over this the other day. And I did say the solutions, there were some pretty good. Yeah, we went over this already. There were some pretty good solutions that they appreciated. Where was it, this fellow? There was a guy who had a very concise, yeah, this one. I liked this one. Was it this one? No, it wasn't this one. It was also PCL's solution. Yeah, this one. I thought this was very good. Suits faces flush straight, pairs, pair counts, and then just processed from there. Did some clever tricks. Yeah. Lot more concise. That's pretty. We talked about that already, I think. And finally, parentheses again. Now this is a very interesting question that I would like to go over. Gosh, I kind of wish I had more time to go over it because it's really good. Also look at other people's solutions. So this is a super interesting question. This is very, very like classic kind of a problem. Also the other one with stacks and parentheses. As if we didn't have enough parentheses that we were dealing with here. Clojure having loads of parentheses. Now we just looked at a parentheses problem, and now we're looking at yet another parentheses problem. A family of languages like Lisp having balanced parentheses is a defining feature of the language. Luckily, Lisp has almost no syntax, except for these quote-unquote delimiters, and that hardly qualifies as quote-unquote syntax, at least in any useful computer programming sense. It is not a difficult exercise to find all the combinations of well-formed parentheses if we only have n pairs to work with. For instance, if we only have 2 pairs, we only have 2 possible combinations. These 2 next to each other, and then 1 nested inside the other. Any other combination of length 4 is ill-formed. Can you see why? Generate all possible combinations of well-formed parentheses of length 2n and n pairs of parentheses. For this problem, we only consider opening and closing parentheses but the answer would be similar if you work with only curly braces and square brackets. Or rectangle brackets. There is an interesting pattern in the numbers. Alright, so obviously solved it already. There's some stuff, some test cases they have. There's a very interesting pattern in the problem. And you notice I use some memoization here. Some funky stuff. So alright, let's talk about it. So the deal is, I don't want to give it away, but there's a very interesting kind of expose you can do on this. So first things first, let's just pull up a list here, and let's say there's 5 of these for 3, which they listed here. they gave us. I want to show you something here. 1, 2, 3, 4, 5. So this is a very interesting question. It's kind of a classic problem. In fact, this is a problem I looked at personally about 6 years ago or so, something like that. Maybe not 6 years ago, 2 or 3 years. A few years back, I looked at this problem because I was with a friend and I was like, okay, I need to like prepare for interviews. I'm kind of terrified of interviewing, and I need to practice, and it was kind of a whole to-do. And this is a problem that you'll find in the Cracking the Coding interview series. This is one of them. This is sort of a classic problem, very interesting problem, found in that book. My opinion wasn't really explained. It wasn't explained well enough, but like, you don't really necessarily get it the first time around, I suppose. I think it would have been a lot better if someone actually explained it to me. So the deal is with these parentheses, it goes something like this. You have a lot of different ways that you can combine these parentheses. But it's not obvious at all. Like, if you suppose you were given these these sets of parentheses, right? How would you generate the set of 4? Is sort of the question that you got to answer. And it's actually really not complicated, but it's really interesting solution. What I decided to go with is I said, okay, let me try initially something like recursive, right? So we'll break these up into the different pieces, and we'll say, let's go with this solution. Let's go with this idea. You kind of have to try to solve the problem a few times earnestly in order to really get the full sort of weight of the solution. So what I thought would be a good idea was I said, okay, let me try this. Let me take the previous solutions of parentheses and say, okay, you can either add a parentheses to the left, add a parentheses to the right, or or contain the previous solution within a parentheses. And I said, okay, those are the only possible solutions, and obviously you're going to have some duplicates, so remove those duplicates. And as it turns out, the duplicates are exactly the cases that the left and the right are sort of symmetrical, if that makes sense. Right, so here you have this left to right one that you added a left piece, and then here you had the sort of right to left one that was you added a right piece. So if you remove these now, remove these two, you notice you have 10 plus 3, you have 13. As it turns out, the solution for 3 parentheses is there's 14, not 13. And at first I was like confounded, I thought, oh, like, basically you just generate these 3 cases and then dump them all into a set, and you'll remove all the duplicates and you should be good to go. Wrong. And if you think about it a little bit, you realize that actually you're missing a very important case. It's kind of hard to see it. In fact, I couldn't see it. I couldn't even think about it. I couldn't even realize that there was a case I was missing. But the case is kind of simple. Suppose for a moment that you were to go backwards from what we're going to use to generate these these values. Like, that's really the issue, is that I didn't have a proof that this actually would cover all of the possible correct cases. And the reality is that whatever you generate, you could technically go backwards from to verify if this thing is or is not a correctly sort of, what do they call it, correctly formed sort of set of parentheses. What you realize is that, okay, going backwards, you have 3 options. You say, okay, there's either opening and closing parentheses to the left, opening and closing parentheses to the right, or this thing is totally contained by parentheses. Well, if you think about it for a minute, if you have 4 opening, 4 opening and then 4 closing parentheses, you can actually construct a case where that's not an opening closing to the left, not an opening closing to the right, so whatever's to the left or whatever's to the right must have some nesting inside of it. And finally, not totally contained within the in just two parentheses. So that means you could break it up into two pieces and say both the left and the right piece have to have some nesting. Oh, that's the missing piece. There it is. So, wow, look at that. Amazing. It would have taken me forever to try to figure out what I was missing, by the way. And it did take me forever. I never figured it out. But I realized you can go backwards from your generating function to generate the piece that you're missing. Oh, so that's how you can prove that algorithm was wrong. Fine, but then what is a correct algorithm? Well, let's go back to what we just did. Let's think about that. This missing piece actually is very insightful. So consider for a moment that we have this generating function, and now consider for a moment this idea of what's called a context-free grammar, which is basically a set of producing rules to create a language. And maybe we can actually create this language using context-free grammar. As it turns out, I did look ahead, and yes, that's exactly how you solve this problem, is you use a context-free grammar. You use what's called a deque language. And I'll tell you what it is in a second, what that context-free grammar is. But you may notice, maybe we can split this up into two pieces, and the rule will be there's a piece to the left, call it S, and then another piece to the right, also called S, and let S just be any kind of well-formed set of parentheses, right? Sequence of well-formed set of parentheses. This is sort of where the production rule comes into place with respect to context-free grammars. And then suppose for a moment that we want to go backwards somehow. So we're not going to just keep splitting this up into two pieces, or where we won't really get anywhere, because we'll just have, well, actually, first off, it doesn't actually handle the case where you have nesting, right? So in order to handle nesting, just suppose that the empty string could be a well-formed sequence, which it is, and then now suppose that the left side is going to be nested parentheses. So it's going to look like this, sort of S nested with S concatenated, where S is any smaller, or just any, it doesn't need to be smaller, but just any well-formed set of parentheses. And then you realize that you can now handle the nested case, because so this case would break into two pieces, where this is sort of S and nested again, right? So this is the rightmost S, this is the opening and closing parentheses, and this is the leftmost S. And then these match, this leftmost S matches, because you have the opening and closing parentheses, an empty string, and another empty string. So that matches, that's well formed. And this guy matches because this is opening and closing with this guy, which we now know is well formed inside, and then S being an empty string on the outside. So this rule actually does properly not destructure, but reverse the generation of this to verify, reverses the generation of this case to verify if this is actually a valid case. And it works, it's true. That's amazing. And yeah, this is basically the rule that you use, as it turns out. You just pair up these two possibilities, and that's sort of like a Cartesian product that you take over these possible sets. So if you have n opening closing parentheses, then you want to have range from 0 to n minus 1 sized sets of S, and then concatenate this whole piece with what's possibly left over. So if you have 0 to n minus 1, you're going to have n minus whatever you chose minus 1 as the sort of this set of those parentheses. And you loop over all those different possibilities, and you get everything you need. And that's amazing. So you can use this to prove that, and you can prove this in the abstract too, that obviously by induction this will work for any well-formed set of parentheses. Clearly you can, if it's broken into two pieces, meaning it's not totally surrounded. So there's really two possibilities, right? It's either totally surrounded by brackets or not. If it's totally surrounded by brackets, then you can use this as an empty string and remove those brackets and recurse on that sequence. So now you can suppose a case, you can repeat that until you get a case where it's not totally enclosed by opening brackets. Well, if it's not totally enclosed by opening brackets, then it must be on the left side enclosed by opening brackets and on the right side enclosed by opening brackets. In other words, there's a split point. Well, now you can use this again to recurse on the left side that is enclosed by opening and closing brackets, and on the right side using strong induction, that's already well formed because it has fewer opening and closing brackets. And so actually, just by strong induction, this does cover all possible cases of like easily. All you can show that this does include all of the well-formed parentheses. And then you maybe also want to show that it also is only the well-formed parentheses. And the reason it's only the well-formed parentheses is that the only time you match parentheses is when they're that actually can show directly is that, well, clearly this is well-formed. If S is well-formed, then S encapsulated as well by parentheses is well-formed, and then concatenated with S, again, that's also well-formed. The whole thing has got to be well-formed. That's actually pretty easy to show that it's only the well-formed. So so this will match any well-formed. It'll match at least all of them, and then it won't match more than all of them, right? Because we just have to prove that this is always well-formed. Sort of yeah. Is that correct? I think so. Yeah, given any well-formed sequence, it will match it, and then the only and then the only things that it produces are everything that it produces. So everything that is produced by it is well-formed, and anything that is well-formed will be produced by it. There we go. That's what you want to show. You need to show both directions. That you don't have anything that's outside of well-formed, right? So that means that it's both it's a subset and a superset at the same time, which means it's exactly the set. So that's it. So you can use this as a context-free grammar. You can prove this kind of easily, that this covers all the cases. Whereas my original idea does not cover all of the cases as described. And so then you could just code that up, and that's what you end up with. Now you also end up with what's called the Catalan Numbers. If you were to count these values, this language, if you were to enumerate it, it has a very clear counting function, actually constant time counting function, which is or closed form counting function. I call it that way. Say it that way. And it's the Catalan numbers, the sequence of Catalan numbers. It's very interesting as well. Also interesting is how do you enumerate, if you are given a context-free grammar, how does one enumerate the sort of the size of the language described by that context-free grammar? That's another very interesting question. Like, you can go from Deque language. By the way, Deque language is more of just like a formalization of what we're describing here. It's exactly what I was just saying. It's sort of this sequence, the empty string as well as S surrounded by brackets with another S. It's concatenated. It's just the production rule for the context-free grammar, and then you can count. Then you can count. In theory, you can use some maths on the. In theory, you can use some maths on context-free languages to count them. Now, I don't know how to do that. I'm not familiar with that. A colleague, not a colleague, don't call him a cohort, I don't know what to call him, but someone who is rather critical of me in the past, but a student, I guess, not my student, but someone, I don't know what to call him, I guess we'll call him a peer, or a colleague of mine, or a peer of mine, once sort of pointed out to me and or criticized me too, that you could solve some very complicated counting problems by creating a context-free grammar and then applying some kind of maths on the context-free grammar in order to derive a like a closed form solution to sort of count over that language. I didn't really understand, and I still don't really understand and really get it, but apparently it can be done, and you can apparently use, this is, I guess, one way to understand it maybe, is to consider the Catalan number. How do you derive the Catalan numbers from counting the Deek language, which is defined by this context-free grammar? There's got to be a way to do it. I just don't know it, don't realize it. There's probably a description of it somewhere. Someone probably figured it out. You could just go look it up and read it. And then there's probably other examples of things that are sort of languages, context-free languages, that you could count, I guess, words of a certain length in that language. I guess that's really the way to do it, is that given some n characters of that language, how many strings are there, unique strings that have of that language with that number of characters? That question. It's a very interesting question and kind of useful for counting, I suppose. Very interesting, very useful for there's the Project Euler questions, have a lot of sort of combinatoric questions that are rather challenging, and I think you can employ that technique probably in a lot of those cases. But anyway, so yeah, pretty interesting overall, and something I kind of a hole in my knowledge of combinatorics, but I'll learn more about that later at some point. How to do this sort of counting languages stuff. I think you can do some pretty interesting results. Definitely one of them is deriving the Catalan numbers for the Deek language. I think that's really interesting if you can use counting context-free grammars. This representation theorem seems to be useful, but I'm not really certain. I'm not really totally clear on what this even means and how this applies and all of that. Anyway, so yeah, there's sort of a lot of depth to this question, and this is a lot harder, this question, than meets the eye, because you would kind of try, maybe initially you might try like a regular kind of recursion that you might do, and this is a pretty simple recursion, but you have to recognize that it actually applies to like better described as a context-free grammar for a context-free language, and then figure out what the production rule is for that. Now, when I was learning this years back, when I was, after I when I was starting to look for work, I was looking for jobs, and I was thinking, I need to be able to pass these interview questions. I looked at this problem, and I just didn't fully understand the solution. I did see a solution that was given way back when, and I didn't get it. I didn't understand, and it obviously didn't stick with me, because my immediate thought was to try the other idea, and you basically will never figure this. Not that you will never figure it out, but it's kind of hard if you don't know this already. It's pretty hard to figure this out on the fly. I have noticed or realized or learned that a lot of the questions that are asked of you are kind of unfair, in the sense that you kind of just need to know them. There's really no figuring them out. And they say they just want to see how you think. It's that doesn't really make sense. It really doesn't. You're not going to figure out the Catalan numbers. Excuse I'm kind of speaking loudly here. You're not going to figure out the Catalan numbers just on the fly in 15 minutes, or where they come from and where they're applied, and that you could potentially use the Chomsky-Schutzenberg representation theorem for context-free language that I don't even know if you can. Still have to learn that to count the language, and I don't know, even just knowing that you could use a context-free language to recursively derive certain sequences of strings is like kind of out there. Not that you couldn't know it, and not that you couldn't be asked, and not that you couldn't figure it out. It's like, it's a pretty unusual thing. Like, you wouldn't just figure that out on the fly. Like, you'd have to really be like aware of these things, that they might ask you a question like that you have this at your disposal, that you can program this recursive function to do this, and so on and so forth. So anyway, I did want to see the solutions though. So I'll show you my solution, and then we'll look at the other solutions. So mine, I used memoization, and I did it pretty explicitly. It was like, okay, parens of n, you're going to say this function f just takes a function g, which you're going to later, it's going to be itself, it's a memoized version of itself. It's going to be binded to this g. I realize it's kind of confusing. You could just assume it's just when you see this GG, it's just calling itself, really, and it's a memoized version of itself. But it's really just, imagine it's calling itself, just recursive. So if you're less than or equal to 0, you just return the set. Otherwise, you're going to have this possibilities thing, which you're going to push the possibilities into a set, which, I guess it's necessary. It's not totally necessary now that the way this is. Yeah, I guess it is kind of necessary, because we are going to get a lot of duplicates, I think, potentially. And then you just loop over all the possibilities, and you say, okay, we're going to loop over this range of values from 0 to n minus 1, and we're going to say, okay, get all the possibilities that have that many parentheses, all the well-formed, this is recursive, right? This is strong induction we're using here, employing. So all of those those different possible sets, right? We're gonna loop over those possible sets, and then for each of those sets, there's going to be another set of sets that we loop over as well, and those are defined by, recursively again, by the difference from n and whatever number we picked here, and then we're also going to subtract another 1 because we don't want to loop infinitely here. So this will always be 1 smaller than our target, and then this is just, so basically if we add the number of parentheses here and the number of parentheses here, it's always 1 less than the target, because we know we're going to add another 1 here. So it'll be n minus v minus 1 plus v, which is just n minus 1 overall, no matter what v we select. And then there you go. You just concatenate this sub parentheses and the sub parentheses, this well-formed smaller set of parentheses with this other well-formed smaller set of parentheses, and then throw in a parentheses on the left side. And that's it. Super straightforward, super simple. Obviously the memoization makes this a little bit faster. So you only need to calculate this one time for each iteration. It's constant time for all n. It'll be constant time, these values, to calculate them, to return them. Looping over those sets, on the other hand, though, will not be constant time. That'll take a lot of time. The Catalan Numbers, as it turns out, is exponential, so this is an exponential time algorithm after all. But it is concise and correct and simple and works nicely. And I guess it is kind of interesting what other people put together. Let's see, 0, I, P of I, K, I, J, K, and then, oh yeah, okay. Oh, it looks like, into a set, yeah. So yeah, he wrote the same algorithm, but just super condensed, way more condensed, and then also he didn't memoize. Excuse me. I could have made this more condensed, but obviously I decided not to. Yeah, it's almost exactly the same. It's effectively the same thing. Yeah, but 0 return this case, otherwise return this case, which is just looping over the subcases as described and pushing the and creating the string and pushing this into the set. Yeah, one lookup of the Deek language and you can realize this is pretty, not that it's an easy problem, but it's relatively simple, but it's definitely not obvious at all why this is like, why it's this way, I guess, or it's not immediately obvious. It's obvious once you see it, but it's not obvious at the outset. So yeah, this is just a condensed version of this, and I'm not sure. This is probably similarly condensed. I'm not sure exactly what happened here. Not that it's bad or anything. It's just different. I'm not really going to go into too much detail because this is sort of simple enough. But yeah, that was a really interesting question too. As if we didn't have enough parentheses. So yeah, we're done with learning Clojure here. We solved all the problems. We're good to go, man. Now we can program whatever we want again, I guess. Program to our heart's content. And we've got feel good about being a completionist here. I still haven't solved all of the HackerRank problems and all the elite code problems, but we can always go back for those, those problems. But I definitely like doing this more. This was more enjoyable. The questions were a little more sort of classic kind of questions, also a little more like, like I said, Clojure seems to be the language of programmers who are extremely experienced, like guys who have like 10 to 20 years experience. I don't have 12 years of like professional experience where I'm getting paid by somebody all 12 years, but when I was 15, I was programming, for other, not, I don't want to say professionally, but like I was getting other people asking me to help program stuff for their games. And I did program some stuff, but I did win a competition for something I programmed, which I think at some point I'll display that online, but that's from 12 years ago. It was really cool, but yeah, I've been programming for a long time, and so I feel kind of at home, with this, and I've seen it in a few places that like Clojure seems to be sort of like really, really invested programmers seem to be interested in this language, and I can see why. It's extremely satisfying, I would say, once you kind of put it together. It's like there's a lot to it that I really appreciate. Yeah, and I can kind of tell from the problems that I was going through that they're really well done. They're really well manicured, as opposed to like other websites. Like if I go on, HackerRank, or if I go on the other one, LeetCode, or there's a bunch of other ones too. But those two, I've been using a lot recently, and I've noticed like the questions are just kind of a little substandard compared to these ones, like kind of by a noticeable amount. It's not so much that it's not like all of the questions, but it's just kind of this like quantity over quality sort of aspect where these seem to be like a lot of quality questions, whereas the others seem to be like, like I said, like I actually didn't find one problem on this site that had like genuinely bad test case. There was only one test case that I thought was kind of unfair, but then I realized actually the way I had written my algorithm was just kind of weak to that test case. Even though my algorithm was correct, it was just a little too slow for that particular approach. And if I had thought about it some more, I actually could have optimized. I actually ruled out the optimization that would have solved it fast enough or preemptively without even realizing that I did that. So it was actually I was actually grateful for that test case. Whereas with other test cases on HackerRank, like, they're just literally broken. Like, it's just the quality of the problems, quality of the authors were just kind of sub par to the quality of authors for this site. And it's like, well, I actually did solve like probably thousands of problems now, over 1,000 at least overall total, and I think I'm sort of qualified to make that judgment. Like, I kind of have enough data to really know that, like, yeah, I just went through 150 problems on the site, and they were all high quality, like quality, good quality. Whereas I went through hundreds of problems on the other sites, and I did run into problems that were just like painful to go through, to walk through, to address, and to look at, and to sort of work through all the edge cases and all of that. Yeah, just kind of not very satisfying overall. That part of that may also have been my abilities. My abilities have kind of increased quite a bit. So if it's become a lot more comfortable to sort of walk through the uncomfortable edge cases. But even more so than that, more important than that though, are like the bad test cases, I'd say, are just kind of, they're pretty miserable. And then, I don't know, there's sort of questions that you get that are just like, I don't know, just really awkward maybe, something like that. Not too, not difficult because they're super interesting and kind of difficult to figure out, but difficult just because they're complicated and difficult. I don't know. I don't really know how to express it exactly. There were a few problems on this site though that were a bit like awkward, I suppose. I mean, going through programming problems on these websites, you do end up with a lot of awkward questions. I don't know. I mean, overall, I thought it was good. There was one question I thought was kind of... Let me see if I can find it. There's this tree question. This reparenting tree question really, like, bothered me. I don't know if I went through the different solutions. This took forever. I mean, this really just took me, like, days. I really struggled. We'll go over it again because I wanted to see what were the quote-unquote better solutions that people had. Yeah, I think I remember this being, these only worked on these test cases. If you assumed that the tree that you're reparenting, it's the same node that you're manipulating. In other words, like, there was sort of A, B, and C nodes, but there could have been A, sort of B sub 1 and B sub 2 and C as the nodes. And in these test cases, it was always A, B, C, and so you can kind of flip around on just those three nodes. Whereas if you had A, B sub 1, B sub 2, C, you had to manipulate things differently. And I ended up with way more code because of that. And it was also way more confusing. And yeah, it really took me a long time, whereas here you could just do sort of 9 lines if you make that assumption. Yeah, there was this kind of complicated. This question I kind of disliked because it was sort of really complicated, or at least it ended up being complicated for me. Yeah. Yeah, some people did it in 6 lines, but wow, that's kind of crazy. He uses this quoting. It's kind of fancy. I don't even remember what that does. But yeah, I kind of would like to. There's a part of me that doesn't mind, like, just kind of going over more code other people put together to solve these problems. Like, this is, mine was like 100 lines of code. This is like 6 lines of code. Talk about breviloquent. Yeah, there's definitely, like, coming back to these problems and trying them again, like a year or two from now, and just going through them. probably has some value, you know. Like sharpening your skills again. But wow, jeez, man, holy smokes. Yeah, I'm almost certain that all of these solutions made this the same assumption, and then it was a lot easier to reduce the problem. 4 lines of code, whereas if you don't make that assumption, it's way more involved. And it's kind of hard to reduce it to just a few lines of code. I mean, I don't know. I'm kind of conflicted. I think I have to maybe have to come back to this problem, review it. Because if I saw this problem again, I'd probably write it 100 lines of code again. Probably do it exactly the same way. But yeah, there was only a few like really awkward questions. Like that one kind of threw me through a loop. There's a few of them that kind of got me. But overall, high quality. I wouldn't say it was really necessarily a low quality question, but it was just kind of one of those like just difficult because it's complicated, not so much because it's interesting, I guess. Which there's many questions like that on these programming websites, but I think there's a pretty healthy ratio of like more interesting questions than more so than complicated questions, especially for the more difficult ones. And there's also an element of like how familiar are you with that question in the first place? If you're super familiar, then it'll be easier, and it gets easier as you get more familiar. And then if it's not familiar at all, then it's just But yeah, that's sort of all things in life. I like that. Familiarity just makes it way easier. So yeah, that's it. That's it for the Clojure. That's it for today's stream. Kind of just go full screen for a minute or two here, and those are sort of my closing thoughts. Yeah, it was like 6 weeks or so we spent learning Clojure. Pretty big, not too bad. Definitely a lot to learn, I guess. Cool thing about Clojure is you can do your whole stack start to finish in the same language. You can do the front end, you can do the back end, you can do the database, you can do everything, which is pretty cool. And there's loads of tools. I think I've shown this on in the past of the Clojure toolbox. There's loads of stuff that you might need. This is pretty good to know, not just to know Clojure and to like have things available, but just knowing what all these different technologies are gives you a lot of breadth in terms of like what you're able to program. I mean, this is just even knowing what all these things are is good, and being able to use them. I could probably go through most of it. Let's see. I don't know. I could probably maybe make a whole video just explaining every one of these in short detail. But yeah, I don't actually know all these things though, by the way. So maybe be an interesting exercise to do. But yeah, I mean, obviously these are all things, libraries and such that were written in Clojure. You can import these. But here's different databases that are Clojure-based databases. Datomic is a Clojure database in and of itself. It's a little more, this is like production quality. This is like something you would use at like a company, like a major corporation would pay for the license for this. This is not free, by the way. Some of these are free, I think, but this one is not. Yeah, there's even machine learning stuff in here. Yeah, there's a few machine learning, libraries. It's pretty cool. Pretty neat. Yeah, definitely attracted to Clojure as a language because it just has a whole boatload of utilities and such and tools. But I do think it does suffer from all the same problems that all languages suffer from, which is just experience, skill, experience, familiarity. Like, you really can't write. People go on and on about maintainable code, and I was like that for a long time too, where I was like, yeah, man, you gotta code. It's largely read more than it's written, and you gotta write it really well, and you gotta make things, maintainable and blah, 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 blah. And the fact of the matter, the reality, the truth is that how maintainable your code is largely depends on the person who wrote it. Someone who's super experienced with the language and super experienced with the domain, and had time to maybe even go back and refactor the code, that code is going to be extremely manageable and, sort of almost delightful to work with. Whereas someone who's like just pressed for time and they're already given a pretty unmaintained and unmaintainable code base to begin with, and just kind of shoved under with all kinds of work and all the nasty things I may or may not have seen recently in my employment that kind of make you cry as a programmer. Not cry, but kind of die inside a little bit. Oh shoot, I'm sorry. Did I do this right? I keep forgetting it. I'm full screen. Oh no, I'm not full screen. Yeah, all those things that kind of make you die inside a little bit. Definitely. Definitely think a lot of it comes from, like I said, experience. It's just kind of like time, Got to get more familiar with the problem. Got to get more familiar with like the pain points and the automation points and the code itself. Which parts can and should you refactor, and how should you refactor it, and make it more readable and extensible. And if you have opportunity to generalize the code to make it more general. Actually, a colleague of mine, coworker of mine, sent me sort of a series of questions about like code quality, and I gotta say, like, I appreciate him sending me that. It's good, but I do really believe it really boils down to familiarity and experience. Because like all of those other things, the questions that you would have about, because there was a whole boatload of questions he had, which were interesting. I mean, it was curated, the list of things that like what code quality questions you might ask. It was a good list, curated list, but answering those questions effectively, like with a resounding yes, this does sort of have the foresight into like future usage and read like future maintainability and extensibility and readability, and the intuitiveness of it, and the brevity of it, and how complecting it is, and how much other components it needs to connect with, and stuff of that nature. I don't even remember the whole list of questions he had. Some of those things aren't actually what he asked. Those questions, I gotta go read it. I'll read it a few times, I think, remember it, what those questions were. But there was also a notion of like the mechanical sort of usage of what you're working with, like how does it flow mechanically, something like that. Like there was sort of a lot of pieces to it, and which I guess maybe is an analog to like the ergonomics of using whatever piece of technology you just put together for someone. All that stuff. I mean, all that stuff really, in my opinion, comes down to like experience and basically doing it wrong a bunch of times, realizing you could have done it better, changing it, and repeating that cycle over and over again until you've got something, it just slowly gets more and more refined over time into something impressive and quite enjoyable to use. See, I realize I'm kind of rambling on here, but it's a meaningful thing. It's a meaningful thing for a developer. So anyway, yeah, Clojure. There's my ad for Clojure. There's my month, 6-week sojourn into the Clojure sphere. I could go start applying for Clojure jobs, I guess, if I want to. I think the next step for me is I'm probably going to, I could maybe make a video about like the Clojure toolbox, explain every one of these things in gory detail. I think I'm also going to look to write a trading program. So I have a machine, a Unix machine I bought that I can upgrade now, put the networking stuff inside of it, and then what I'm going to do is look to Arch Linux. Look to upgrade it in such a way that I can program automate my trading, right? So I have a trading account with a sort of e-broker, and like I said, I could have made $1,500 just today, if I was a little sharper about my trading. So I'm thinking it's too much stress. I don't like feeling like I lost $1,500 because I missed an opportunity. I'd much rather just have an automated trading program go and just let that trade on my behalf, and collect my 2% each week of whatever I'm trading. If I can get 2%, which I think I can. I think I can consistently make at least 2% a week of my invested money, which is actually an insane amount. 2% each week is like pretty wild, but I'm fairly confident I can make at least that. Yeah, that means I'll be making like 280% of my investment each year, which is, I think I can actually do better than that. And then, as I make money, I can just throw more money in, and it kind of compounds and stuff. And it'd be pretty good. And then eventually we'll look into maybe doing asset management for other people. Like if other people have some money they want to invest, and then I can start run the program on that. And then I could even start looking into more refined methods of sort of electronic trading. There's stuff with like machine learning that you can do. I mean, there's definitely the particular approach that I'm looking to take. I definitely could run machine learning algorithms on to try to piece together what how I might want to trade. Although I get this kind of uncomfortable feeling that the machine learning algorithm, what I end up learning is that exactly what I already knew. Like, I basically get the same result, the same determination. But the market's more or less random, but it's got a lot of volatility, and so you can take advantage of that. It's like some parts of the market are sort of always going up, so you just get a general sense of its upward trend, and then you can just trade on the band as it pops up, as it goes up. Yeah, it seems lately the markets have been trading on just the news alone. You could do that too if you can do like sort of a news analysis type of thing. You kind of just consume tons and tons of news and get a sense of how people feel about the general market. You can trade on that too. But like I said, I mean, I already knew all that. Like all I have to do is read the news and then trade on that. And then it's like, why'd you spend all the time building a machine learning algorithm to do that? It's like you already know what's gonna happen. Yeah. And I would be even better at it than a machine learning algorithm, because I happen to know people well enough that I know, because people are the ones that trade. I would happen to know that their perception, what they probably would perceive, what they probably would think. Like, oh, Trump signs a new trade deal with China. They probably think that it's going to be a boon to the economy, so it's going to shoot up way higher than it should. Not because the economy actually improved at all, but just because of speculation about like what people think is going to happen. Which, teaching a machine learning algorithm that is like kind of difficult. It's kind of hard to explain that to a machine. Overall, explain that to anybody else. Explain that to myself, but not so much to a machine. So anyway, I don't know. We'll figure it out. So thank you again for watching. Talk to you all soon. Have a good rest of your day. We'll have more things to come here. Probably gonna vary it up. Probably gonna go for machine learning algorithm, not machine learning algorithms. Just simple algorithm to trade on my behalf, so I don't have to be like ever watching the market, because I just hate doing. I'll just be honest. I don't like trading. I like making a lot of money, but I don't like the stress. It's ridiculously stressful. Especially today, where like instead of making $1,500, I made 10. It's like, come on, it's killing me. And then the other one is oh yeah, speed running. I've taken kind of an interest lately in speed running. I think it's cool. It's fun things you can do with games, like basically tie your hand around your back kind of stuff, and it's like how do you do getting an AI program, machine learning program to like do pull-ups with its hands tied behind its back, kind of stuff. I think it'd be a lot of fun. Could look into that, how I can make those things happen. I was searching around for like GPUs I might want to kind of explore this endeavor, this series of ideas. We'll see how all that goes. But yeah, speedrunning, I think, like older games is probably not such a bad idea because the games themselves are relatively simple in terms of like what's going on in the game, and they're also extremely consistent. So I imagine it wouldn't be that hard to write sort of like machine learning for older games. Sure, machine learning stuff. One more detail. Oh yeah. Gotta get my computer hooked up still. That server that I'm gonna use, but yeah, automate my trading, and then maybe make some YouTube videos about like trading and about Clojure and programming the trading bot, and maybe programming a little bit with that machine learning on like applied to games. And then I don't know. I guess at some point I'll start depending on how the trading goes. I kind of want to give it like a few months of like just let the automated trading go. See how I do. I think if I give it like a few months, I can come back with the results, and then I could say, all right, can start managing money, ready to go. Could be a good time. I don't know. We'll see. But yeah, all in all, good things to come. So thank you again for watching. Talk to you all soon. That's it for the foreclosure problems for a while. Probably not going to come back to that site for, I don't know, probably a year or so at least. I definitely do want to come back to this idea of like counting problems using context-free grammars. I think it's pretty cool. I mean, there's a whole boatload of problems I haven't finished yet. I like Project Euler, and I've solved over 100 problems on this site, and they've got almost 700 now. But there's some pretty good ones that would there's kind of a lot of maths involved with this stuff. And I'd say if you could solve all of these problems, you've got like a pretty good like combinatorics background in maths. Excuse me, it's kind of esoteric, a lot of this stuff, but it's very good. I mean, it's really impressive if you can solve these problems, in my opinion. Yeah, I definitely appreciate these questions a lot. They're really hard though, overall. Like you gotta be like pretty talented, I think, to solve all of them. Have like a really strong sort of breadth of knowledge. I don't know. I'm kind of conflicted about spending so much time on these because they're, like I said, they're just extremely, they're just really difficult. They're kind of impossible to do, at face value. You kind of need to research a lot about maths sort of in general, and then apply these more esoteric ideas to the problems. That's kind of really the way to do it. You're not really able to like solve them directly. S of nm be summation of the totient function of n times I for I less than or equal to m. This is Euler's totient function. This is kind of interesting. This is actually totient function has a property whereas n times I is totient of n times totient of I. So this is actually the totient of n times the summation over the totient of I, and then the summation over the totient of I is probably could be reduced further to something simpler. And you're given that this 510 by 10 to the 6th is this number. Find by 10 to the 11th last 9 digits. I think you may be able to do this by hand. Totient of n is simple, right? You can find that one. Right, that's a relatively small number. I mean, even 11 digits, the totient of n it shouldn't be too hard to calculate. And then 10 to the 6th is the summation of the totient from 1 to n. Actually, you could probably do all these directly. I'm not sure how hard it would be. 10 to the 6th you could brute force. This 10 to the 11th, I'm not sure if you could brute force that. These are supposed to take under a minute, I think, the problems. Your calculations. 10 to the 11th won't take a minute. But I think you can do some tricky shenanigans with divisors here. To simplify these totient, you could probably... you could really actually reduce this problem to just the summation of the totient of I over the totient of I. Oh, wait a second, is I and M, yeah, M is the big one, yeah, so the summation is the interesting one. So you'd have to figure out, you can maybe do some tricky shenanigans with divisors, like common divisors, because the totient function is really just, basically it's a function of the divisors of the, I want to say it's a function of the prime divisors. So really you can get all the primes and do something here. It's n times, I think 1 over 1 times 1 minus 1 over piece of 1 times 1 minus 1 over piece of 2 quantity times 1 over 1 minus 1 over piece of 3, etc. for a given value n. So for I, so I'm given I, it depends on the primes of that I. Yeah, it's kind of tricky. There's some, I think there's some, what do they call that? Some, what's that called? Not maths, but there's some, what do you even call it? There is some theory that you can apply to this totient of I summation. I think you can do this relatively easily overall. I think you just kind of gotta think about it a little bit more. But yeah, there's a lot of really interesting questions on this site. Really appreciate this website. But it kind of requires a large breadth of knowledge that it's just kind of difficult to accumulate all that without being like a PhD or something. And it's a lot of time. It's just a lot of time. Like I think I'm probably better off pursuing other things in life, like starting a family, being a big one, having kids, finding a place to live. It's not absurdly expensive. Things of that nature. It's probably better than spending all my time looking to solve these problems. So yeah, again, thanks for watching. Talk to you soon. I feel like I've said that 3 times now. Have a good rest of your night. Take care.